So dynamics can be defined as the part of mechanics that study the forces and their effects on object. So force is measured in newtons and it is a vector quantity. So force unit is newton and it's a vector quantity. So therefore it has both magnitude and direction. So you're gonna treat the force as a vector quantity. So when you try to add them or subtract, remember your vector addition and vector subtraction. Okay. So an important thing to note is knowing to write free body diagrams. Okay. So used to organize forces acting on the object. So just identifying the forces acting on the object. Okay. So you will simply, you can represent a particular object by a dot. So you don't have to draw. If you're talking about a person, you can just use a dot, okay? Or a box sometimes, if you want a box, but most commonly, I'm just using, like, if you have an object lying. So for example, what would be the forces acting on this box here, lying on the surface? So if I gonna draw my free body diagram, so I gonna represent my object as a dot. So this is my object. This is my object. So you just have to draw the dot to represent your object and identify the forces. So uh, as I mentioned earlier, this particular object on Earth, well, it should be acted upon by gravity. So Fg is downward. Okay. And I know that it is lying on top where it is on a surface. So what force is that acts on a particular object that is lying on the surface? Is it not that we call that one as normal force? So there will be normal force. And it is away, if you can see, it's away from the surface. So the surface exerts also a force on the object in this particular case. And we will make an assumption that all the forces are acting on the center of the object. For every force acting on that object, draw a vector arrow. So again, that is just the arrow that we make here. So that. So, and also this. So it's just a straight line showing the size and direction of that force. And label. So the label, you can use symbols for this. Just use symbols. Symbols, e.g. So for normal force, if you're talking about normal force, you don't have to write normal force. You can just write Fn. Okay. And numbers are not necessarily written there. Okay. And the resultant force is the vector connecting the beginning and the end of the arrow. Well, this is just the same thing as when you say resultant force, this is just the sum of all forces acting on the object. And yeah, same thing as before. If we talk about resultant, you just take the sum. But remember that if you take the sum, you need to take note that 10 newtons north plus 20 newtons east is not as simple as adding their magnitude. Okay, so you have to remember that. Again, this is a vector quantity, so therefore you try to treat them as a vector quantity. Okay, so let's take some examples here. This is on writing or drawing the free body diagram. So we want to draw the free body diagram of this object here. So I'm just going to represent my spaceship or the rocket as a dot. So again, this is my rocket. Okay, so you can just use a dot to represent the rocket. And by the look of that, it's just lying and sitting on a launch pad. So it's not moving. Okay, so again, this object here is acted upon by gravity, Fg. And what else? Well, it's lying on top of a surface. There must be what you call normal force. Okay. And since this is not moving, you can assume that the magnitude of the normal force is equivalent to the magnitude of Fg. Okay. Since rocket is not moving, magnitudes of Fn. So again, I'm using the word magnitudes. Magnitudes of Fn is equal to Fg. Okay. So again, I would say that one because again, it doesn't move. It is not moving. So I would say that their magnitude should be the same. Okay. So okay, let's take for example here. This is the same rocket, but now the rocket is moving upward. So the rocket fires its engine and flies upward. So it flies upward. It flies upward. And let's say, for example, this is accelerating upward. Accelerating upward. So if I'm going to draw again my rocket, the free body diagram of the rocket. So I'm going to represent the rocket again as just a dot. Well, even though it's flying now, it's still acted upon by Fg, or the force of gravity. There must be weight. And then what makes the rocket flies upward? Well, this is due to the engine of your rocket. So there must be F thrust or applied force with that. And if you can see, this is now longer. This should be longer. So this is your F thrust. Okay. So F thrust is greater than F thrust is the magnitude is greater than your Fg. This symbol here just indicates that I'm talking about just the magnitude. Okay, the magnitude of the thrust force is bigger than the magnitude of your gravity. Okay, let's take example number 3.
Sorry,
yes.
teacher.
Yes.
Example 2, I think you need to depend on the time. Because when the rocket starts to fire and when the rocket are in the constant speed,
yeah, if it's
their
constant,
balance is different. Yeah,
yeah,
the balance
yes.
is actually different.
Yes, that's why I places the word there, accelerating upward.
Yeah.
To just to, yeah, I know that
yeah.
somehow, if the magnitude of your thrust force is equivalent to the gravity, it's no longer accelerating. It's moving
yeah,
constant velocity.
yeah,
So let's just say that it's
yeah,
accelerating upward. So that would be
okay,
bigger. Okay.
okay, I know it.
Okay.
Thanks.
Yeah. You're welcome. So let's take example number 3. Use the free body diagram below to determine the uh, resultant force. Uh, let us just say this particular force, the magnitude of this and this are equivalent. Okay. So if you're gonna add them, is it not that you're just trying to, if you have F1, again, the resultant force is just taking the sum. Taking the sum. And graphically, what you're gonna do is just like, if you have, how would you add F1 plus F2 plus F3? Okay. I'm taking note that F1, F2, and F1 and F2 have the same magnitude. Okay. And F3 is this one here. Sometimes I'll just, well, if you can see here, these are bold letters, because some other books, instead of using the arrows on top, they use bold letters to represent a vector. But that's quite hard to write down here. So I use the arrow notation for vectors. So if you're adding, is it not that that is just, you go up, so F1, but if I gonna add the vector F2, I gonna start drawing it from the tip of my F1 and then downward. Since you have equal magnitude, that means that that just cancels out. And that is, this is F3. So therefore, the resultant is just equivalent to F3. So the resultant is just equal to the magnitude of F3 in this case. Because if you can see, this is canceled out. So the resultant is just the sum. Well, if for example, if we will give some values of this, like say F1 is 10 newtons, and since they have equal magnitude, this is also 10 newtons. And let's say this is 20 newtons here. So mathematically, remember that when you take the resultant, you can only take the sum of all x values and sum of all y values. Okay, so that means that for the x values, I only have positive 20 newtons. If my to the right is my positive, the y values here is let's say for example going up is positive, you'll have positive 10 newtons, then minus or plus the negative of 10 newtons. If you're gonna add that one up, that's 0. So that gives you 0. So therefore the resultant is just equal to 20 newtons. So the resultant is just equal to 20 newtons to the east. It's east, right? Okay. So if you can see here, remember that I cannot add 20 to 10 and 10 because that is on a different component. That is in the y component. So remember that when we do vector addition and vector subtraction, well, specifically in this case, because we're taking the resultant, the sum, we're just taking the sum of all x component and the y component. And if we're creating a right angled triangle, that means that neither of the x or the y are 0, in this case, the x value or the y value is 0. That's why your resultant is just equivalent to the x value. But in the case wherein you're creating a vector that has a particular angle that is lying in both x and y component, that means that non-zero x and non-zero y, yeah, that could be different. We use the Pythagorean theorem then. Example number 4 here. Draw the free body diagrams of the pictures below. So forces acting on the sled. So remember that the question is the forces acting on the sled. Your sled is this one. This is your sled. So we want to know the forces acting on the sled. So again, you can represent a particular object with just a dot. So I'm gonna do that one there, a dot. So if I'll be writing forces acting on this one, let's say for example, let's take into account the friction between the ice and the sled in this case. But for sure, just like before, you always have your FG, okay? And it's always downward. Well, if the object is, excuse me, if the object is moving, so its velocity, let's say for example, it's moving in that direction, okay? If the object is in the moving to the left, friction would be to the right. So this would be the friction. This is my FF. Again, if you can see, the surface is here, so the frictional force is always parallel to the surface. But I would expect, since I applying a force there in the direction to the left, so it would be moving to the left. And another force that is present here is that it is in contact with the surface, right? And that contact force is what we call the normal force. So we have the normal force that is directed upward, okay? And then what else? Well, this particular person is trying to, with the use of a string pulling in that particular direction. So therefore, you have there a tension force in that direction. Okay, and that is Ft. And remember that since it is the string that is attached to the sled, so therefore the force acting on this object is not necessarily a force exerted by the person directly, but it's actually the force coming from your tension force, and the tension force is directed in that direction. So yeah, I think that would be all the forces acting on the sled. Any question about this one here? Remember that if you're drawing a free body diagram, you're gonna concentrate on a single object. And in this particular case, the question is the sled. The one that is being asked is the sled. So you're talking about this object here. This is your object, the sled. So you're gonna examine the forces acting on that. And again, there would be gravity, there would be friction, there would be normal force, and the tension force. Okay, for the figure at the right, From here, I think this is Son Goku, right? Or from Dragon Ball.
It's Vegeta.
Oh, okay. So yeah, so he's trying to push the box, okay, on the wall. So forces on box push against the wall, uh, so that it does not move. Because I think you have noticed this one. If you have a book, if you're gonna push it on the wall, if your force is not enough, the pushing force that you exert, it will slide down. So let's say, for example, in this case, the force that is being exerted, well, said there, it doesn't move, so it stays there. So we can again represent the object is the box. So the box is your object. Now I'm gonna examine what are the forces acting on the box. Well, an obvious one is your gravity, because that is directed downward. Okay, there must be gravity, and it is directed towards the center of the Earth. And since Vegeta is pushing it, so there must be a pushing force, and that pushing force is to the left. Okay, so I'm just gonna call that one as Fa, the force exerted by Vegeta. What else? What other forces do you think is acting on the box? Because for sure, in the particular sense, this object will be moving, because if you can see, the forces are not balanced. So there must be other forces here.
Friction.
Friction. Okay.
Friction. Yeah,
uh,
because of gravity, it will goes down,
mhm,
but because it's touched the wall,
mhm.
so the friction will be upward.
Oh, perfect. Okay. Friction must be upward in this case. This is a common mistake by students. Like in this orientation, they try to make the upward force as your normal force. But then again, that's not the case. Because remember that if the force is not, the applied force is not enough, this will slide down. And if you have a sliding motion, remember that friction would be on the opposite direction. Okay, again, you have in contact the box and the wall. So your wall is your surface in this case. And in this particular case, if you're being asked, where is the normal force? Well, normal force would be to the right. Okay. And since this is not moving, we're gonna learn this one.
Yeah, because the hand is pulled on the box, so because of the press, so the normal will be the opposite of the pressure.
Yes, yes. So remember that normal force is the force exerted by the surface. This is what I mean that we need to familiarize the different forces, because commonly the students will try to write their friction to the right and then their normal force as upward. But then again, we go back to definition of friction and normal force. Well, these are contact forces, and friction is always parallel. In this case, your surface is the wall, so this is your surface, and this is your object. So when you try to draw the different forces, it should be something like that. And this particular symbol just indicate that this must be equal to the magnitude of this, and this should be of equal magnitude with Fn. Okay. So are there any question with this one here? So it takes time to actually familiarize these things. I know that, but this is the first step. You need to know how to draw free body diagrams to be successful with dynamics. Because Newton's law, which is our next discussion, the first law, it's not talking about a single force. It's talking about the sum of all the forces. Okay. So when you take sum, again, that is just the resultant force. You try to add all the forces.